Share screen. All that good stuff. So we need a different lesson than that one. We need the rest of that one from yesterday. Unit 2. Courses. Motion. Everybody can hear me? Yes?
Yeah, we can hear you.
Thank you. Always good to check. All right. So let's just do maybe a tiny bit of attendance here. Zealous.
I think Kayla's coming over. She's still in the other meeting, but I just told her to join this.
Oh, yeah. Fair enough. G. Donaldson. Gates. Oh, Margot right now. Or do I have to go to the list? Margot. Page. So it looks like I'm missing Dawson and Margot, is that right? Right now. If you see either of those join in, please let me know if I don't notice. So the first assignment is marked, but I haven't published the feedback on it yet because I'm missing some of those from 3 people. I believe I have emailed those people to notify them that they need to hand that stuff in, and that fairly soon I'm going to be releasing those results, and at which case a new assignment will be sent out for people that didn't do the first one. I'll just be picking more questions to give, and yeah, hopefully they'll be about the same difficulty level, but there's never really a guarantee. So you might want to get that in as soon as possible. I think there were only 4 submitted for the current assignment, so more than 3 people have that little warning meaning something to them. Any questions about page 27, 15, 16, 19, 21, and so on? The solution set for it is all ready to go here as well. For the most part, hopefully you found those fairly straightforward, where you're just picking an equation and calculating out answers. It makes sense. With the equation method, you got to be pretty diligent and careful about assigning directions for things and keeping things consistent. But the solution set that you see there now is pretty straightforward, where you pick an equation, plug numbers in. Was there one where I had to pick and solve for the velocity first instead of having to do quadratic formula? I forget whether there was one of those or not. Oh, and I just put the textbook shows 2 significant digits. That one I kept the 3 because they'd given us 3 all the way along. Anyways, no questions? All right. So here.
Sorry, can we take up the last one quick?
Number 24?
Yeah, I think so. It was like the one with the reaction time and stuff.
Oh, yeah. So number 24. So the reaction time problem. I'm surprised I didn't do a VT graph for this one because it just helps visualize. I thought I had shown, maybe I showed it in class yesterday or something, so I feel like I've done it already. But yeah, because I remember showing the reaction time and then the slowing down to a stop, right? And so you're going to have to think of like a calculation to do with this section here, which will be constant velocity, that section. Let's go, blue for the constant velocity section. And then of course you've got like a uniform acceleration kind of calculation for that section while you're slowing down. So what did I put here? Just gave the information they gave. Initial velocity, it's a total of 48 meters to the stalled car. So I put, yeah, so that bit you're going to have a total distance you're going to travel while the reaction time's going on, and then of course a distance so this right here is basically that blue section, and this is the green section in that picture up above. So the first thing I did is I just calculated out how far, actually, reaction time, I gotta just remind myself what they said in the question. Did they say what the reaction time was? No, they're asking what the reaction time is, that's right. So the displacement you're gonna travel during that reaction time though is this, the velocity times the reaction time. And then we know that the final velocity is 0. The initial velocity is of course the 28.3, and we know the acceleration, and we know, well, we can solve for delta d basically, right? How far you'll travel while slowing down. So basically we need this distance you travel while slowing down, plus this sort of unknown, but it's known based on variables, distance you travel while reacting. Those need to add up to the total of 48 in order to just stop on time with your bumper, kissing the bumper of the stalled car, but not damaging. Yeah, so solve for delta t. That make sense?
Yeah, that's good. I just didn't get the 20.83 delta t. That's where I got stuck.
Yeah, because you kind of get stuck where you're like, wait, I don't know the distance, but yeah, you just gotta forge ahead, right? You have the courage to forge ahead and have delta d in terms of, right? So in terms of the thing we don't know, even though it's not known, you can still sort of write it out, right? So if someone's had said, the reaction time is 1.5 seconds, will it not hit it? We would have just plugged in a number here, and that would have been fairly straightforward to do. So just the catch of being able to do that when you just have variables is the sort of the next step to get really used to and have be just as easy as plugging numbers in. That's kind of why that question on the second assignment is there. Just in terms of N's and Q's. I don't want you to only be able to do questions and carry out logical steps. You need to be able to do that even if you don't have numbers. And that's exactly what that step here involves. So good. All right, so we are heading on to down here somewhere. Which page did we get to? That was the reaction time question. Was this a, forget whether it looks like maybe that's a one. Anyways, there's the reaction time question worked out as well there. I had mentioned that you want to look through the vectors stuff and make sure you're okay with the idea of, they're going to give you a velocity south and a velocity north. When you go to actually plug that stuff in to an equation, when you plug it in, this is an old solution of this. So I feel like I want to add a little bit to this one to make it up to my current standards, basically. So, you're going to choose a direction reference frame in order to have like this kind of make sense here. So it looks like I'm choosing north as a direction, right? So if I said here, let's choose north as the positive direction, then that means that this one would equal negative 41 meters per second north, right? In which case now we have numbers. We have a minus 41 north and as an initial velocity, and we have a 47 north as a final velocity. And then when you go and do v2 minus v1, I'm just going to do it up here for now. So your delta v itself is going to be v2 minus v1. When you put numbers in, they have to be based on the same direction system, right? So that you can't put in a 41 south and a 47 north and expect logic. So you have to put it in instead as the minus 41, meaning, minus 41 north means south, and then take away that 47 north. And so we'd end up with a negative, take away another negative. That's where that 88 is coming from, because we end up with a minus 88. Try not to hit that little thing, or else it'll change the size there. So minus 88 north. In other words, delta V is really 88 south. Right, so that's the little bit of a catch in terms of the ideas of how you calculate this stuff out. So let me move that down here. That'll work. I'll make it easy to move, and basically an in-between line along the way here to make that easier to. Maybe I'll do it like this. All right. All right. So let's just do that. That way you can see, where the delta V came from, of course, right? Yeah, anyways, so that's something to watch for in terms of just being careful about directions. So make sure to look through those pages as I've recommended, because if you're rusty and having trouble with that kind of stuff, you're gonna want to have that not be something that causes you to get questions wrong in the real stuff that we're tackling in grade 12, such as this type right here. So this new type of uniform acceleration question. Just look at the graphs. We've got car A and car B. Describe those motions first of all, right? You should be able to look at that and say, okay, we've got car A accelerating at a faster rate at the start. They're both starting from rest. Car A is accelerating quickly, but gets to a 15 meter per second velocity and then stays at that velocity. So accelerated motion and then constant motion. Car B accelerates slower, right? But continues to accelerate, ends up going faster in this section. Car's going faster than car A, eventually gets to a constant velocity of 20 and then maintains that 20. A common misconception, a common incorrect interpretation of this is during this section, the car B starts to go faster, right? But does that mean that car B is ahead of car A? It starts going faster at this point. But is it, well, I suppose we should point out the obviousness at the beginning here is that car A and B start from rest, car A accelerates, so it gets ahead. This is the part that I wanted to emphasize first, is that it gets ahead of car B, right? So in that green section there, we would say now, okay, car B is going faster, but is it ahead? Well, no, of course not, right? So let's just put that in there, but not ahead yet. I'm going to put but still behind car A. I need to get rid of that control screen. How do I do that? There we go. But still behind. Certainly still behind, at least at the instant it starts getting faster. And so what we're tasked with in this question, you might sort of be able to picture, is we're asked for like when the car B catches up with car A, right? This, I think I have other slides, other places as well, but this kind of extra area, if we know that area equals displacement, right? That's something that we have a benefit of knowing from having done the VT graph method to build confidence in the equation method. We recognize that that area represents like the distance ahead, right? Distance ahead that car A is than B. So now if we look at this distance in here, right, that now is the car B getting ahead. And so you can probably tell by looking at that this distance, this area here in red one, this is car B catching up. But based on the rough drawing here in the graph, does this area look like it's big enough to be the same as that area? Probably not. Right, so these are the ideas I want you to be able to think through and interpret as you look at a VT graph of a question like this. So car A stops accelerating before car B will end up going faster, car A will eventually catch up and pass car A, car B will eventually pass car A. So this is a catch-up question. This is a new type of thing that we didn't get into in grade 11. I think technically it could have been covered in as far as the curriculum list goes, but I just wanted to move on with the course basically. And I know I'm going to tackle it in grade 12 anyways. So the idea is we want to think about the displacements and so on. This is my note from the other page there about how this one represents how far ahead it got, and then this one's now catching up basically. So if car B catches up while it's going with constant velocity, certainly the math is easier, and that's the kind that we're going to start with. So basically, I want you to visualize that there's some time later on, right, where it catches up, right? And the math, the variable designation for that, I have been using this time around. It's I haven't always used this in the past, but I believe this one is this will be easier for us. It's like, think of the catch-up time as being like an overall delta t. How long until, right? There's your overall time until it catches up. So we're not working with that yet on this page, but we will shortly. But just think about even just the starting numbers here. We have the car A, right? The distance or displacement it goes while accelerating is this part, 1/2 the base times the height on the BT graph. That's just the triangle area. And then the car goes this rectangle I'm circling with my mouse as well, right? So that's from the 30 until the 70-second mark. So that's 40 seconds. So there's the base times the height. So you can see that the car A goes 825 meters up until the 70 seconds. Car B goes the base times the height, 1/2 base times height. There's the 70 the base and 20 is the height for the faster velocity. Car B has only gone 700. And so you can see that car B is ahead still if you're analyzing this way. In fact, it's 125 meters ahead still. Okay. So I've justified that this statement here, that it catches up. It's not just an assumption in this case. Often it will be just an assumption you'll make in a question if it's fairly obvious. You don't need to analyze this out every time. So the trick for this, or the method for solving here, is the main concept. If we're looking for where, right? If we're looking for where they catch up, basically the idea is we're gonna set their displacements equal to one another. When they catch up, their displacements are the same. That's going to be the starting point for answering a question like this. This question, if it was written in words, would have been car A accelerates at a rate of, and they might give the value, or they might say increases velocity to 15 meters per second uniformly over a 30-second time interval, and then maintains the 15 meter per second velocity. Car B, starts from rest, increases velocity to 20 in 70 seconds, and then maintains the 20. You can picture the wording of this as well. And you need to be able to interpret the wording. Any questions so far? So if you're given the wording, you want to be able to graph it. I gave it as a graph because it's almost easier to communicate what the heck's going on, of course, right? If I just start with the graph. So our process, it says here, the key, follow the bold steps for sequencing through this page here. So number one is the key is that when you're passing, or when it catches up, in other words, the displacements are the same, right? So they're at the same spot when the car catches up, when it passes it. I've used the terminology there. So we're looking at the total displacement for the car A, and total displacement for the red there, car B. So how that's going to work, let's just cover up this. I can reveal it bit by bit here, right? So this part here to start out with, we know obviously if we're just going with the logic, we have rectangles and triangles and areas under the graphs. Nice and easy, just go for it. We've got the 1/2, the 30 times the 15, that's the triangle. And then we've got, notice what I've done here is I labeled it as, I probably wouldn't normally do this line, the delta T1, but I have it labeled on here for now. that I think you'd at least be saying, well, this rectangle, if I'm getting to this spot where it catches up, let me do the purple catch up line as I did before, right? So if this is the catches up business, actually it's there, it's all good, right? Then you'd be looking at, well, I need to figure out this value here, okay? So the way that's going to be put into the equation, of course, is your total time of delta t, take away that 30 in order to get the whole amount. Because if the whole distance is 30 and the distance from here, or sorry, the whole distance is delta t, and this portion is 30, then the remaining bit is delta t take away 30. The red car has the exact same logic. It has the triangle, which is a known base of 70 and a known height of 20. So there's the 1/2 base times height. And then you have the height of the rectangle, the 20, times the remaining time, like this time here, delta t2. But of course, we'd list that as delta t minus 70. The total time take away that initial accelerating portion of 70. So we've got an equation there mapped out where it has only one unknown, delta t, and algebra is your friend if you're on good terms with it, and you calculate a number. You get 95 seconds. Therefore, car A catches up after 95 seconds. Catch up question. Boom. Okay, so obviously you're just collecting like terms. I did show all the steps here. You know, take away the 15. I chose to take the 15 over to this side, so I didn't have a negative. That's just something I do more in my teaching than I did as a student, to be honest, because if I took it the other side, and you know, negatives are a common cause for a mistake with student work. So I'm sort of coaching to try to avoid having negatives that are going to mess you up. You know, make a choice, move it to the side where you end up with a positive 5 delta t. Anyways, so that's what we ended up with. Any questions about that one? Do I need a little bit of time on that page? That slide?
Yeah, can you leave it there for a minute?
Yeah, thanks.
Just key your mic and tell me when you're ready. I'm not going right away. I'm waiting for a bunch of people to say, okay, I'm done.
I'm good. I'm not sure about other people.
Yep. We got one.
I'm good too.
Two.
What does it say in like the original equation there, like with the delta t on the right side?
Over here, delta t2 maybe? Is that what you
Okay.
mean?
Yeah.
So I wouldn't even write that line necessarily, except maybe you'd want to have like the 1/2 30 15. Like instead, maybe write 1/2 30 15, and then 15 times the delta t minus 30. Because on here you've got your overall time to catch up, the delta t that I'm going to wiggle here, right? And then of course the initial you're not traveling at constant velocity here for that whole delta t. You have to take away the 30 from it. All right. So
All right. Yeah, that's the part I didn't see.
Yeah, that's why it's delta t take away 30. So I would just put the delta t take away 30 stuff right into here if I was doing this again from scratch. Right here.
All right, I'm good to move on then.
Perfect. All right, let me know if anybody needs any more, but let's go on to here. So we've got the time. If you wanted to figure out where, then of course you can just put the 95 seconds in to either one, right? So if you put it into this is for the car by the looks of it. Obviously we could just do delta d for, so let's do or delta d. This must be A, this must be B, I guess. So the B was 1/2 of, I'm just looking at the numbers here, 1/2 of 70 times 20. Just give myself a little bit more room, but plus, I'll just write it for now. We've got the 20 times the delta t take away. The initial time was It's not letting me. There we go. 70 seconds. So I'll just shrink that all. But yeah, I'm just wanted to show you could calculate the displacement based on either car. So, geez, these are all grouped in weird, wild ways, and fits magically, right? So then, of course, this would batter anyways, right? They're supposed to be at the same spot. So whatever you do along here, that should be the 1200 as well. And this is basically something you could do as a check, right? Not mandatory, of course, but if you have extra time somewhere on a quiz or a test or an assignment or whatever, it doesn't hurt to check and make sure it's true. So that is your first catch-up question. All right. So just going back and thinking about the logic of things and checking things over. Remember, I went back and I did look at the fact that it was 125 meters ahead still at the initial time there. So you could even look at it in a different way where you're like needs to catch up like that extra 125, right? And then the so the 125, what do I have here? This isn't explained very well right now. It's a good thing I'm going over this with you. What's that? What's the 5? Everybody recognize what that 5 is? I'm trying to do a different color here. So basically, I'm looking at the extra velocity, right? So this is the extra velocity. So I'm not really recommending you bother to think of it that way, but it does confirm the idea of how this works, right? So really what I'm looking at in this diagram, let me just gather this guy here, copy and paste. Probably going to get rid of some of it, but all I'm talking about on this diagram with that work there is get rid of some of this. I got rid of part that I actually want there, but I can shade it in again. We're talking about this, right? Talking about that rectangle to catch up, but you had to identify how far you need to go. So I don't really recommend this page as the method. It's really the set the numbers, set the displacements equal to one another is your best way to tackle these on an ongoing basis. But nice little logic confirmation bit with that, right? So the trick type question. Okay, the next type. So catch up with a trick, basically. The trick in this one is that the car keeps accelerating. So the slow car B, keeps accelerating. So it becomes really likely if it keeps accelerating all the way up to like 80 meters per second. If you're doing the math on that, 80 times 3.6, that is 288 kilometers per hour. So this car is going to continue to accelerate until it's going almost 300 kilometers per hour. Quite likely it's going to pass that car while it's accelerating, right? So if you were just sticking stubbornly with the assumption that it's going to pass or catch up while traveling at constant velocity, you can run the numbers for that just like normal, but you'll end up getting that it passes after 38.3 seconds. And so think about the logical inconsistency here. You're saying it's going to catch up over here at some number bigger than 60 seconds, and you get an answer mathematically of a number that's smaller than 60, right? So this just shows that it's not bigger than 60 like your assumption was, and so there's something wrong in the math. Okay, so what's wrong is the assumption. Okay, so you gotta be careful about that. If you get an answer that doesn't make sense, it might mean that it's a situation where it's catching up while accelerating, and so you've made a false assumption. Right? Sometimes math will do that. It'll just give you an answer that doesn't make sense, and you check the numbers, and you're like, no, I did it right. Well, it was the original assumption that wasn't right. So if we are tackling a catch-up question with a trick, let me know if you need time. But our first step, let me just cover up a bit of this here. Our first step is the same logic. We're still saying like let the total displacement for car A and the total displacement for car B be the same, right? But our assumption is more realistic, where we're like somewhere in here is where they meet. Okay, so let's look through what that does. For car A, it's not so bad. It's not so different really. So just pay attention to the left side for now. We got like the triangle plus the rectangle like normal, right? For car B, then your area is just a triangle, which at first glance you might say, oh, that's easier. We have less calculations to do, right? But the problem is, since this location here, so this number here is unknown, that means that correspondingly, this number, the velocity, is unknown as well. We've got a relationship there between these two. So the number here for the time and the number here for the velocity are related, and they're dependent on one another. We have a function there, right? And that's going to be the key on how to figure this out. So let's just tackle this side first to start with, at least. So we got the 1/2 10 times 20, like here, like normal. And then we've got, is this a different 20? Was this a different one than the original one? 1/2 of 15 and 20. Oh yeah, no, it's the same one basically, because we got the 30, 20, but then the red one's just a different one, right? So we got looks like it's 10 and 20 now though. I don't know. Anyways, look at these numbers. You got a car that accelerates at a faster rate up till 20 meters per second over a 10-second interval, and then goes at a constant rate. And the other car accelerates slower, but for way longer. So it is actually a new set of numbers. But that shouldn't be a deal breaker. So this is normal, right? This is delta t minus the 10. So we've got the total time here. Take away that initial 10, so the time to catch up. Stretch that out so it goes all the way to when we're thinking it would catch up. Take away that 10. So that stuff's normal. The trick is on this side. So on this side here, we've got 1/2 of the base, which is the base is delta t directly this time, right? So there's your delta t. The 60 is actually irrelevant in this question, isn't it? Because it's not to do with when they catch up. So there's no point in trying to do some kind of like 60 takeaway or something for delta t. So we're just using delta t as the base of the triangle. We've got the height of the triangle is delta v. It's an unknown, right? How can we get that unknown? Any thoughts? Any guesses? If this was set as like as a challenge question or as an assignment, what would you do to try and figure out this number here, that height, based on this number here? Any ideas?
Could you take away the area under A?
Well, I wouldn't want to complicate. I'm just trying to think about a height here. Like I'm trying to think about a number value for v, right? So I wouldn't want to start to think about areas in that scenario. I just want to use the relationship that we should recognize we know between the time variable and the velocity variable for car B specifically. What do we know about car B specifically? We know that in 60 seconds it speeds up to 80 meters per second, right? How do we say that? Let's just put here, we know car B, right? Speed, like accelerates or whatever to 80 meters per second in 60 seconds. How can we use that known information? So picture this, okay? 60 leads to 80. This actually leads to another way to do this, even the way I'm doing this. But so what does number t, right, this time here, lead to? We could actually just do that using ratios. Totally good, right? You can just use a common ratio there because it's the acceleration rate of the car, right? So we could say, well, I know 80 to that equals this to this, and basically that ratio is equal to a number, and so you could get that common ratio. Like you're going to say like 60 over 80 is going to equal number t over v, right? So we could solve for the delta v and put it in right there. I don't think that's how most people are going to do this, though. I think most people would recognize that we know acceleration equals delta v over delta t. And you say, oh, acceleration equals the 80 over the 60. By chance, I did my ratio upside down, but you'll see that this is the same thing in the end. So acceleration is the 80 over the 60. And then we want to know the delta v for a given delta t, right? So we can solve for delta v, right? Change my color by accident here. So delta v is going to be the 80 over the 60 is the actual acceleration value, whatever that is, right? And delta t. So get that number and plug it in, and that's what you'll see over here. Is that you can, I'm sure I've already kind of described it over here as well, but that's exactly it. Okay. So you got acceleration. What we know is the acceleration of car B. So acceleration equals delta v over delta t right here. And then we're like 80 over 60 is the acceleration. So that's delta v over delta t, multiply both sides by, what did I do there? Oh, that's just, I'm just showing that 80 over 60 is, i.e. that's, saying in other words, that's, I don't feel like I need to put that. But maybe, I don't know, do I? It looks like since I did that over here now, maybe I think it's better. Anyways, multiply both sides by delta t and you get your 80 over 60. So there it is. Right here, the 80 over 60 delta t. That's just acceleration delta t. That's all that is. You might be noticing that what we're talking about is one of our key equations that you practiced yesterday, right? What part of a key equation is this that we practiced yesterday? 1/2 acceleration delta t and a delta t again. That's delta t squared. So really, that's just one of our uniform acceleration equations. Okay, so we've actually developed that before and used the equation many times. But long story short, we end up with a quadratic, and so we solve that quadratic and end up with answers, and we use the answers to claim results. So you get an answer from the quadratic formula that I'm not reviewing at this moment, but can if we need to. I'll come back to this in a second here, but so it gives an answer of 6.3 or 23.6. Well, it can't be 6.3 because that's not based on our assumption. So the 23.66 meets our assumption values, and then you can check your displacements, and they're both 374. So your conclusion is, oh, car A catches up in 23.66 seconds at the 374 meter mark. So let me show the whole page there and let you copy what you need and ask questions if you need. What I put here is, notice the link to y equals mx plus b to, like, this is a straight line. And so it's y equals mx plus b. Well, the y values are the v's. The acceleration is the slope. The time is the x variable. So this acceleration equation, right? It's actually delta there, of course, right? But the acceleration equation matches our y equals mx plus b line from grade 9 even. So you could even tackle this with a grade 9 flare if you wanted. And that's pretty much how the solution needs to go for these whenever you have a catch-up question that continues to accelerate, that is. Does anybody need more time at this point?
Just a bit longer, please. Sorry.
Okay, just let me know then, okay, when you're done.
Okay, I'm good, thanks.
Okay. So just think of these as like something you're going to practice, a few more times, like maybe even just do this exact question again from scratch on a blank piece of paper and refer to help, so that this one should become, easy to tackle first. And then you're going to practice the to catch up where you're still accelerating one, and get that to be something you can just tackle on your own from a blank piece of paper as well, right? That's just going to be a little bit of practice needed there. So that's something you still have to practice yet, right? Another trick is sometimes things, they don't start from the same position. And I put it in terms of a drag racing term. I watched a show one time, and they're betting pink slips on cars, and so if basically whoever wins the drag race gets the other person's car. There was a show about this. I don't know if anybody's ever watched it or not. But basically, if you want to compare two cars and you want it to, if you want to race someone, but it's not about the car, instead it's about how good the driver is, then they do a couple of drag races and they just determine how good the cars are. And then they negotiate how many lengths they're going to give the other person. So the person with the faster car agrees, like, oh, I'll give you 2 car lengths or whatever, to make it fair, right? And so when you have things not starting in the same location, that's the next kind of trick. So this is one reason why it would happen or could happen. But in general, like, it doesn't have to be that complicated. It can just be, a police car, with a motorcycle or a police, like a motorist speeding past. And if it takes this part D here is a catch-up question where they don't start from the same spot, because the police car takes 7 seconds to put down their laptop or whatever, right? Just get the car started and get pulled out into traffic and get going. So this is where they don't start from the same location. And you'll see that in all of these examples that we have. This one's all worked out. This one down here somewhere. We have other examples. Those are all the solutions. Here's the extra ones for practice. Okay, so we have a boy running out the door, starts down the road for school at his normal pace. He usually covers this displacement in that amount of time. So this is the implication here. It's implied that that's constant velocity. 360 seconds later, his mother discovers that he has forgotten his lunch. So she runs after him at 4 meters per second. How far does he get in the 360? Blah blah blah. How far until he catches up? So this question is actually a little bit easier, although different. So sometimes that makes it harder. But this question is all uniform motion, not uniform acceleration. It's like constant velocities. So I didn't check these answers yet, but all the other answers that I worked from on that, where I got this from, were correct. So I suspect these are right. Same thing in a long distance run. Michael's running at this distance and he's this far behind, who's running at a constant velocity of, if Michael accelerates at this rate, how long will it take him to catch up, right? Obviously the one is 75 meters ahead of the other, without it being because of a drag racing scenario. But long story short, we've got different starting points. This question here, number 10 on page 84 of your grade 11 textbook, was thrown in there by the authors. No other mention of catch-up questions at all in the textbook. Boom, there it is. Good luck with that, students. So of course I noticed that and was like, yeah, we're not doing that one right now. But Michael's running, blah, blah, blah. Is that the same one? Michael 15, I don't think it is, but it's like, I think some of the same names or something. Where's that? No, that's the other one. This one here. Michael, it is the same question. There you go, 3.8, I think so. Anyways, I have the solution for that one worked out. 3.8, that's funny because I got them from totally different places. And it's just obviously someone's taken it from the textbook or the textbook's taken from that place, whichever the case may be. But what would we do? So what's the logic of this? Like, Michael is running, blah, blah, blah. He's 75 meters behind. I think it's pretty clear that Michael needs to run 75 meters more. Michael needs to run 75 meters more. Right? So, clearly that's the case, right? So what looks a little weird in the equation work here is if you had delta D Michael and you had delta D, if you said equals delta D Robert, this is what we used to do, right? If we want them just to go end up having the same displacement. But if they had the same displacement overall from where they started, Michael would still be 75 meters behind. So is it intuitively obvious to you that you'd have to add a 75 here? Basically what I'm saying is Michael's displacement equals this, 75 meters more than Robert's. Okay, so that's what you need to do. I think I remember as a student looking at that, and it's like, but I'm adding to the person who's already ahead. But no, it's like Michael's needs to equal 75 more than Robert's, and so that's how you calibrate this thing, how you set it up. Okay, so a catch-up question for not at the same spot is the third kind of grade 12 version to tackle. Okay. So let's go full screen here and page width or whatever I should say, and go through it. So here's the given information, obviously, like normal, write down your given information, maybe draw a graph to visualize things. The problem with the graph is you can't see the 75 meter head start business, right? But so for the first portion, you can tell Michael's falling behind. Eventually, Michael starts to like catch up, right? So catches but then Michael catches back up to being 75 meters behind. So I have like, you know, this triangle fell behind. This triangle, if it was the same size, it's not quite, but if it was the same size, then he got back to being 75 meters behind. So basically, we have like a final question here, almost if he dealt with it like that, where he needs to travel 75 meters farther. But that's just kind of thinking our way through it. The end result is what I said here, where we just say Michael's displacement needs to be 75 bigger than Robert's. Boom, there it is. So we've got basically a normal catch-up question with this extra 75 tacked on. And I put there, I know it sort of looks like we're adding to Robert's, but Michael's equals a number. We're adding to Michael's number basically to give Michael's number be bigger. So normal stuff, we've got the 3.8 and we've got the 1/2 base times height stuff for the 3.8, because I think that I'm thinking here, oh, just delta V over delta T, basically with an unknown delta T and an unknown delta V, right? So that's in. The acceleration is going to go in as normal. So I'll just denote here. So basically this is unknown, but we can figure it out from here. Right? So that, like I said, that really is your 1/2 acceleration delta T squared equation. If you're comfortable with just noticing, like, oh, accelerated motion, go for it. Initial velocity is 0, right? So that's your equation. V1 delta T plus 1/2 acceleration delta T squared. So I'll just leave it with the red there. And Roberts was just 42 the whole time, so it's super easy, right? He's going the same velocity the whole time, so there's plus the 75, and so basically we have a setup here with only delta T missing, and so you gather up the variables or collect like terms and put it in standard form. That's your A, that's your B, and that's your C. I'm being careful to take the negatives with it as well, but the quadratic formula gives the solutions to that quadratic, and you get an answer here that either Michael catches up to Robert before he started racing, 29.1 seconds before he started racing, or the more logical answer, he catches up 34.4 seconds after trying to catch up. Clearly, this answer is not logical. It doesn't catch up 29 seconds before they started racing. So the only part from this that was new was the 75. So I'm hoping that gives you the skills needed to sort of tackle this. You're going to go look through this and get good at following the ideas of that and be able to do it yourself. Okay. So there is another example all worked out. I don't know. We're probably better off letting you see this page for a little bit. Is that what we'd say to do here right now? I don't know if that's going to work though or not. Is that too small for you to be able to see it on your end?
Yeah, it's a bit too small.
Okay, so do we need this page still though? This slide? Should we leave this?
I think personally I'm okay. I worked out a different example, so
Okay.
I think I'm good.
So no one needs this slide anymore then? Okay. Okay. So this one's all worked out as well. I don't want to just keep going on the same type, so I'm just going to leave that for you to go through. Although I have to, what I'll do is I'll clone that page so you can sort of see the idea of it. But on the second page, have everything revealed. But then there's your usual. This, by the way, this first question isn't starting at a different spot question, right? So it's just your normal stuff. The more recent solution works through, so you might find it a little more consistent. This page is dedicated to the whole conversion from kilometers per hour to meters per second stuff, if you're wondering why the 3.6, if you've forgotten. And then this page, again, I'll just clone, maybe I'll just do this after the fact, so we're not, doesn't take long here though, so I'm going to do it. But that's just checking to make sure they're the same displacements and so on and so on. But I'll finish the job on this. Just have to remember to do it. Anyway, so there is another type that we need to tackle. So the other type is a meet in the middle type or an intersect type. So I want you to think about that one for a little bit. Read this one, think about it. So I feel like this question is different enough, even though it's kind of the same question. It's different enough that it would seem, if this showed up on a test instead of a regular catch-up question, I think I'd have some problems, right? There'd be some questions. Can we reason our way through it right now, though? Maybe more than one way to tackle this thing, but what do we think?
I don't know, probably.
Okay. So the hard part for this one would be, I think it would be awkward to try and draw the VT graphs and so on. Somewhere I had done that, but it doesn't appear to be on this solution of it. Oh yeah, it's up here. That's right. Oh, you know what? I apologize. Bounce around on different slides. I went too far. So I'll go back up to the one that delivers this a little bit more consistently. So there's some other examples as well. So there's a 3-second head start, right? So determine, the head start amount, basically determine how much extra distance is needed. And you're going to see that extra distance in somewhere along here, the 18, right? The extra 18. So that page will be there for you to work out as well. That's just another example of this kind of thing. So lots of examples worked out in here to, help you. So this is the main intro page for the other type. So the intersect or meet the middle type. So in these questions, things start out a distance apart, and the motion of each reduces that distance apart to 0. Once that distance apart is reduced to 0, they meet. Right? So I kind of like how this worked out actually, because I got us thinking about the idea of it, right, in this Romeo question, and then we're thinking, okay, I think that's going to give us something to do. If you look back at this Romeo question, I'm going to be saying like let the displacements add to 0 is basically the idea, right? So set those displacements, like you have the distance apart, and then take away the distance the one person goes and take away the distance the other person goes until once that becomes 0, then they've met in the middle. So this one here, let's do this one first instead of the Romeo question, because this one I have the VT graph that is there, but basically here I'm saying, yeah, we've got this one person that's traveling at 10 at a constant rate, and then we've got, that's Edward, E for Edward, not East. Philippe or however they want to pronounce that, accelerates from rest at a certain rate. So there's the acceleration graph. And one of these is north and one's south, and so the directions are kind of hard to show on the graph. So I'm probably not typically going to draw the graph, right? The key idea is to show that they're, to know that they're both reducing the distance, and so that's the key here. So the original distance apart to be reduced to 0, that's what we need. So both motions are taking away from 30 meters. So we're setting 30 take away the distance or displacement Edward has, take away the displacement Philippe has, and saying that needs to be 0 for them to catch up. So why don't I give you a little bit of time to do some legwork there and see how it goes for you. I'll give you a little bit of time to copy the question down and put a good heading on it, because this is definitely one you're going to want to refer to for help if needed. So you can tell for Edward, you just have constant motion. So it's just going to be a velocity times time, a 10 times a delta t. Major surprise there, I don't think. The 10 times the delta t, whatever. I just had it as variables first. And then the other one, of course, is going to be a triangle. So our ease of use of this thing. So I've jumped right to in this one that 1/2 acceleration delta t squared equation, because after doing it a few times, you recognize like, okay, well, instead of doing 1/2 base times height and then plugging acceleration in, why not just cut to the chase? So we've got that equation, and delta t is the only unknown, and it's a full quadratic. So you're going to need to do the quadratic formula. I think it's in the shed. There it is, there. So full quadratic formula gives you results. Gives you a minus as usual and a 2.8. So the 2.8 is the logical one. So there's Edward and Philippe running to each other.
Why is Philippe's displacement with a half and a square on the delta t?
That's the usual. So Philippe, I'll show it a little better here, or again, I should say. All right, Philippe, delta d, Philippe is 1/2, darn it, 1/2 delta t, delta v, as usual, right? Area underneath the curve. But then we don't know delta v, right? So, but or whatever we're saying, luckily we know it, I guess. Erasing here. We've got acceleration equals delta v over delta t. I'll move that back in a second here. Delta v over delta t. And so we are solving for delta v, getting acceleration delta t, and that is plugging in to there. And then that gives us 1/2 delta t times acceleration delta t, which gives us 1/2 acceleration delta t squared. That is what I used there. So think of your uniform acceleration equations, like really what we're using is the v1 delta t plus 1/2 acceleration delta t squared. And so it's this part because this is 0, right? So with the first part of this just being 0, you're left with just the 1/2 acceleration delta t squared. Does that help?
Yeah, I don't know why. I just thought they would be like the same for some reason.
Yeah. So this is that same process we went through in that previous slide, but it's just, getting used to it, I guess. Go ahead there. New question.
At the bottom when it's the QF, what does that mean?
Quadratic formula.
Oh, okay.
Yeah. Okay. So review how to do the quadratic formula. Make sure you can get 2.8. Sarah, with your fancy calculator that you're you got as a gift there. You can get the quadratic formula results directly with an app in it, I bet. If it automatically has it, I'm not sure. I can help you with that later if you want. And I would say as a whole for this class, okay, we're listening carefully, as a whole for this class, you absolutely want to make sure you're able to do the quadratic formula. If you're not, that's pretty bad, right? You got to be able to do the quadratic formula. Do you need to endure doing the quadratic formula every single time it's needed in a physics class? No. As long as you know how to do it and you know you could do it if you needed to, then you can just use an app on your phone for that matter. So it used to be, I was like, the people that had the TI-83 calculators and things like that were lucky because they had polysimult on their calculator and they could do it. But you know, I haven't actually done this in advance of this lesson, but I bet. Let's look at quadratic formula solver. I've never done this in my life, but I bet it is a very easy thing where they're probably going to have a little applet somewhere that's going to be, you know, you're going to put in your A, B, and your C. Boom, there it is. Big surprise, right? So let's go to quadratic formula here, and we're going to put in a negative 0.25, negative 10, and a 30. Negative 0.25. Negative 10 and a 30. And this is exactly what I did on my calculator to get that answer. Calculate. And it's going to say, oh, okay, so you get an answer of negative 42 and 2.8. That comes from doing the quadratic formula, of course, right? But, you know, if you're able to do the quadratic formula consistently, then save yourself some time. Just slap down the answers. I know I can do that later on when I need to on a quiz or a test. Follow me? Yep. Good. I will.
That's great.
Yeah, I think that's a big time saver, obviously, right? So let's go back to when I first got to this page. I don't know if the link changes or not. So let's go to here, and I'll just copy that link in case you need it. But you know, obviously, like I said, I quite literally have never actually done that. Googled, but it occurred to me yesterday when I was thinking of trying to remember to tell you, Sarah, that you can use your calculator to do that as a little shortcut. And then I was like feeling bad about everybody else, and I went, wait a minute, we're living in the future. We can just Google it, right? So boom, there you go. So this is, you know, like I said, if you graduate from Rito and go off to somewhere and can't do the quadratic formula, that's going to be kind of embarrassing. So don't embarrass yourself. Be able to do the quadratic formula, but you know, get the answers in a more efficient manner after you get good at it. So this example of Romeo is the same thing. We got the distance apart, take away the distance Romeo, and the displacement Juliet and Romeo both do, and they add to 0, and that means they've caught up. Okay, so that is the other type. So I've got that page all ready to go where the solution is shown on the next one. I just need to do that for a couple of these ones, then I'll save and post that one. Kind of think maybe that's only one lesson, but I've got some people that want to get caught up on assignments, so I am going to stop there against my better judgment. But we do have a lot of review going on, right? More practice, do regular uniform acceleration, look over that vector stuff. I am counting on you to be able to, they say V1 is this and V2 is this, and they ask what's delta V. You need to be able to say, oh, delta V equals the tip to tail, you know, tail to tail subtraction actually is the wording we would use, right? So you'd have the tail to tail subtraction. Like there's you know, a fair bit of grade 11 stuff that I'm not right now, right? So if this one is the initial, reviewing it slightly right now, I suppose, but if this is the initial and that's the final, then guess what? That's delta V, right? And so by scale diagrams would be the starting skill level method, and then of course components and so on. You know, even sine law. So this would be like components. Oh, computer does not like me. Components or sine law, cosine law, sine law, cosine law, etc. Right? So just make sure to look over all that kind of stuff. And when there's problem solving that involves these kind of steps and questions later on, I hope you have brushed up on those and will have success in those, because I am giving you time to do that right now. Dealio?
Sounds good.
Yeah.
So I will get these slides ready so they're easy for you to look at or help. That one's already done. And yeah, that's it for today from me. Part C. Seriously. C. Part D.
Thank you.
I'll stick around here and planning lessons and stuff like that, so I'm easily accessed for till noon, of course. But you don't need to stay logged in if you don't want to.